Alright, so I'm here with my Google Pro student plan, and I'm asking a studently question here about some really it's a dumb question I could probably Google, but I'm using Google V2 right now, which is Gemini 2.5 Pro. And I think I've been given a little A/B test here. So I've been having fun just reading these and just enjoying the fun of reading the same thing twice in a column format. And so, we can start reading here. Yes, absolutely. You can definitely train a model with one learning algorithm and then take the resulting weights and continue training them with a different algorithm. The final weights will be influenced by both training stages. So my question is already answered. And this is sort of why this question is so dumb, because it's pretty obvious that that's already the case, right? Just in the names of pre-training and post-training. But, I've already completely cognitive offloaded into the LLM system, so I'm not even going to think about that. I'm just going to ask it for the answer. Because that's what learning is, right? All learning is just getting the answer and memorizing it. I'm just kidding, of course. So learning is basically trying to do it over and over and over again on your own until somehow experientially it all comes together. So I think like in this parallel reading style, you read one paragraph and then like you should probably take a chunk and then take a chunk, right? But what you're going to find is you get sucked into reading down. And that's good. What happens when you get sucked into reading down is it means you actually understood the thing you just read well enough to be able to advance into the next chunk. So that's good. So it's like you go down when you understand, you go over when you don't. Okay, so what I think this is Gemini 3. And so you can read this one. Yes, absolutely, you can definitely train a model with one learning algorithm. It's the exact same sentence. And then use the resulting weights as the starting point for another round of training with a different algorithm. So that's the same exact sentence. This is a very common and powerful technique in machine learning, often called sequential training, pre-training, or fine-tuning. So this is what Karpathy is letting you do for $100 with his new Nano GPT, Nano Chat. Papa Karpathy. So Papa Karpathy says these are the same thing pretty much. This is just 2 paragraphs, and this is 1 paragraph. This is the same chunk though, right? Maybe, I don't know. I don't know what I'm talking about. So then you get a little bit more prep thinking before it goes into a practical example, it seems. And this one goes straight into how it works, which I think is also this. So probably they both have a how it works section. Let's get into that. So let's go back. How it works, 2-stage process. Think of it building on a foundation. The first training regime uses one learning style. You then take the weights from stage 1, use them as a starting point for a second training algorithm. Fundamental powers, features, and dynamics. How? We're just accepting it. The weights are adjusted to get good at a broad, often unsupervised task. Example from your systems, you could use contrastive learning. Okay, so and here's the example from your system. So this is just a more stretched out version of this, I think. Which is good. Like this should be more verbose if it's better, right? Right, guys? If it's a better model, it writes more, right? It learns the fundamental physics and causal structure of your 2D world. This is exactly what we're going for here. So this example from our system is articulating exactly what I've been trying to do. So that's very good that it has identified that the weights are now encoded with a rich general purpose understanding of how things move and interact. But to be honest, contrastive learning distinguishes between real and fake game sequences. And to be honest, that's like probably not enough information for me. So I would just make a little twine in the loom and send one off to basically explain what this training really is and how it works. So let's go back to here because it's saying the same thing now. The weights in a neural network are just a large set of numbers. I think that's a better introduction paragraph than this. The first training algorithm adjusts these numbers to get it good at a certain task. The second algorithm simply starts its own adjustment process from where the first one left off. I think this is just way better written, I think. So this is just a better introduction. You know, I think a good essay, right, and any good presentation of information, you give it at the dumbest level it possibly fucking can be. You can definitely train a model with one learning algorithm. So that's just the dumbest thing you can, that's just like the dumbest understanding. It's just like, absolutely you can do it, right? If that's all the details you want, you're good. And then as you delve in deeper, you are presented with more details in a increasingly complex cascade, right? So this is the most simple understanding of it. This is a little bit more in depth, talking about how the weights work, how to adjust the weights, and how these two interact with each other. So similarly answering the question. Now going into the details that they did over here. Stage 1 pre-training. Stage 2 fine-tuning. I mean, it didn't name ours as pre-training and fine-tuning here. Or I guess maybe it will down here. So I think this is an analogy like that I'm not sure is actually that good. I don't know enough about the topic to actually say that this is a good analogy. I mean, it makes sense like on a deeply analogical way, but sometimes like analogies can be so broad that who gives a shit, you know what I mean? It really matters about the accuracy of it. So take a block out of marble and chisel out the basic shape of a person. I mean, sure, whatever it did. I love LLM philosophy because it's not logically coherent. It's like patterny. Like I've had some really funny conversations talking about like, you know, esotericism and, you know, mystic ideas and, you know, like different gods and their responsibilities with LLMs, and it has some really funny like mix-ups and non-connections. Like sometimes it'll just cross the wires a little bit about two gods and their responsibilities and then recombine them in, you know, interesting ways. Like, for example, I was comparing one character to Thor and then another character to Odin in this anime, and it kind of crossed wires halfway through and then just it turned them both into Odin. And I was sort of just thinking like, oh, that's kind of cool. It's just taking like a shit ton of different mythological stuff, like father, son, you know, father eating the son, son killing the father, and then amalgamating them into like some holy trinity, you know, religious thing, and which is just a cool emergent property of the field, you know, of comparative religion, where it's sort of like you're literally looking for patterns all the time with that. So then it seems like the structure of LLMs would be so suited for just blending all that shit together into like a fucking red penguin smoothie. So here's a better example of contrastive learning, which is exactly what I asked for here, right? Oh no, up here. So don't read the left, it's a spoiler. Oh, no. Okay, so we can read the left. No, we can read it. Okay. Phase 1, pre-training, offline broad knowledge. You could use a self-supervised method of contrastive learning to learn the fundamental physics and causal structure of your game without any specific goal. So this would feed the model thousands of hours of recorded gameplay. Yeah, fucking right. The model would learn to distinguish real game sequences from fake ones. Sequences where the player teleports, move through walls, or objects disappear. I mean, that is more fundamental, actually, than the original RLI was, the original training I was trying to apply, which is, verifiable by prediction of collisions between objects. So I think this model would be able to I think, identify that through this condition. Moves through walls. Yeah, movement, collision, and object permanence. I think that is probably what we want. But just for fun, we're probably going to ask it to do this kind of phase 1, phase 2, phase 3, phase 4 for like a shit ton of different learning methods, and then use them all exemplified in this little simple game that I'm using. Which I think is probably like, I don't know, this is the way I've conceptualized the best way to learn it, is just like try and build something with it and then look at your example that you understand relatively well and then put that example into all the other things you're trying to learn. See how it works. It works for this specific situation, yes. All right, let's read fine-tuning then. Yep, this thing again, we know about that. Yeah, we get it. After pre-training with contrastive learning, you could feed those weights into the model-based RL Dreamer system. The Dreamer model doesn't have to waste time learning basic physics from scratch. The weights already understand that. It can immediately focus on the more specific task, learning a policy to achieve goals like avoiding collision within that physical world. The final set of weights is a composite of both training phases. The initial structure is provided by the first phase, and the target refinements are made by the second. Now you take the pre-trained weights from trade 1, so more brief. This is actually a little bit more educational, I guess, but this does have this goal process result structure, which I guess is easier to parse. I don't know if this counts as LLMification of text, but I think this is actually a good use of like structure, paragraph structure. It's just a little bit boring when you do the same 3, but I understand that it's also useful for imparting information. So it's not always about entertainment value of the writing, of course. So I think this is better. This is just like the same information, but yeah, these are both good, honestly. These are both fine for me. They actually sort of differ. So to train a specific policy, this is sort of like we start with the goal, and then here we're talking about the goal at the end. Process. The Dreamer model uses pre-trained world model to dream or simulate future outcomes. So this is not really mentioned here. So process information is not really mentioned. Because the weights already understand the game's basic rules, it can learn the specific task of collecting gems incredibly quickly. So that's really good because I don't know if I mentioned it in my question. No, I didn't. But I think previously in the context, we're sort of talking about this idea of doing things very fast, doing things in runtime rather than in a training phase. So I mean, it seems suspicious that I didn't mention it up here somewhere. Yeah, here. Transfer learning, pre-training, and fine-tuning. It doesn't mention that in between pre-training and fine-tuning, or maybe, after all of it, it's that as the simulation is running, you have to do at least some basic heavy learning. But that's not really the point of this exercise. We're just trying to compare this, so sorry for getting off track. Now you take the pre-trained ones. Okay, yeah, so they're teaching me better here for sure. Result, the weights are further adjusted to be highly effective at the specific task. The general knowledge is still there, but now fine-tuned. Great, thanks, man. This sucks. This doesn't, I mean... No, I'm sorry. This doesn't suck. But this doesn't tell me anything new. The weights are further adjusted. The final set of weights is a composite of both learning phases. I think this does say it better. The weights are further adjusted to be highly effective at a specific task, because that's what we were dreaming about. Or were we? Were we dreaming about a bunch of different examples, or were we dreaming about specific task? So I need to learn more about Dreamer to answer this. So these are sort of differing opinions here from Gemini. Unless I'm wrong and I'm misunderstanding, but... it does say specific task here, okay. All right, whatever. I'm just tripping. This says the same exact thing. They're both fine. This is both good. Whatever. These are the same exact thing. Just different order. All right, we got a little emoji here. Got an emoji. They dropped a brain emoji. Thanks for that. So good. I think it would be cool if I can use emojis in this game as art, as game art. Sort of one of the biggest goals is to like somehow steal people's emoji assets so they don't have to download anything to play the game. Just in like a cybersecurity fucking meltdown on their fucking Apple storage device. And then I can use the brain to like build a little like Mr. Krabs type enemy character, and this will be what his hands look like. So it's a massive speed increase. So, I mean, this is like so obvious, right? Like I already knew all this from LLMs. I just didn't fucking formalize it because I don't think anymore, because I just talk to LLMs for my answers. The truth is that I already knew that LLMs have base models, right? So what I'm building is a base model that understands the physics of the world. And then on top of that, I'm slowly adding more models like, collision detection models and basic reward models for opening a chest, and then enemy stuff, and then further and further more advanced models to predict player fucking gameplay loops and reward them for, sniping or charging in heroically, or, assisting their friends in trouble, right? Another digression. So this is a finished off here with a list. And it seems like they have the same elements. Massive speed increase, dramatically faster training. It isn't starting from random, ignorant, straight is more descriptive than learn the basics from scratch. But it does sort of mean the same thing. We can reduce the time needed for a new task from days to just a few hours or minutes. And then we've got an analogy here. Which is cool. I think we need to just sort of think about it a little further here to actually generate a more interesting answer. What we really need is like a further inference, because we're talking about different phases. We need a sort of chart, an inference that perhaps it would be useful to have a chart of all the different training methods and then their cook times, basically. So we have to do a calculation of trade-offs where it's like, which is going to give me more accuracy and which is going to give me faster runtime. And then we're going to want to get up to the threshold of base model where it's like we've trained it to the highest quality over the longest period of time. And then we are sprinkling on again, I'm using this fucking cascade analogy, but cascadingly complex, more efficient methods to do at faster inference points, like on game pause or, frame by frame. So, and this is how the use of a project that you're building can help inform the questions that you ask to facilitate your learning. Like I wouldn't have the impulse to ask, oh, well, what about a different method, if I wasn't building something that I was interested in. If I was just memorizing all the different types of learning and all their different costs and benefits, I wouldn't be so invested as I would if I was trying to pick out which of those methods is going to best serve my specific needs in this specific situation. In both of those cases, I need to acquire the exact same knowledge, which is a good comparison of all the different options and their trade-offs and benefits, right? Better generalization, more robust. Great. Robust is always good. So I wonder where I got the brain emoji here. I guess unseen. I don't know. Combining strengths, improve performance. Same thing. The foundation from the first. It is so interesting, true, when you do this exercise of comparing two different LLM generated essays, is it's like, dude, words are fucking interchangeable. I think something like 50% of them are. Improved performance, combining strengths, better generalization, all kind of mean the same thing. Combining strengths, improved performance, better generalization. Improved performance and better generalization are different. Improved performance and better generalization are different. Because generalization in and of itself is a type of specialty, whereas improved performance isn't a specialty. Performance kind of means nothing. Like in this case, we're talking about performance in that we're stopping it from getting stuck. Whereas improved performance could also totally mean a massive speed increase. Or improved performance could also totally mean a reduction in compute usage. Or electrical, Or it could mean the quality of the results are better. So combining strengths means bringing together different specialties, which means generalization. Okay. You can use a powerful but computationally expensive algorithm for offline pre-training and then a faster, more agile algorithm for real-time adaptation. So this is exactly what I was talking about. So this isn't combining strengths. Well, it is, but because everything is. But what it is, more specifically, is optimizing for different opportunities to use each model for its best use case. Data efficiency and fine-tuning the base model for different objectives. So like the question that you have to ask when you get little lists like this, summarizing your query to an LLM, is you have to say, like, if I took all 8 of these chunks and I ran them against each other, how many chunks would I have left? If I wanted a list of unique chunks. And I'm so tempted right now to copy paste this whole thing into a fresh tab and ask it how many chunks there are. And that's the pull of the fucking devil, man. So I'm not going to do it. I'm going to sit here on this TV, my computer, instead of going outside. Because the devil is the call of the outside. And I'm going to read all of these even longer. And I'm going to try and learn what they mean. And I'm going to compare them. Massive speed increase and dramatically faster training. Both have bad initial names, but what they're actually talking about is, well, whatever. We're talking about jump to competency. We're talking about achieving of the goal. Sure, the model trains faster, but what we're actually trying to say is that it doesn't start from nothing. It's not about how fast it trains. It's that it skips. It doesn't have to train as much. That's what we're saying. It's not that it trains faster. It's that it doesn't train as much. And I could be wrong, but that seems like my synthesis of what's actually going on, right? If we have to train from scratch both times, I don't know which model is actually going to be faster. But since we're only training the very last end of it, then this one technically, this phase 2, stage 2, technically in time goes faster than stage 1. Not that the actual model learns faster. But these are still trying to say the same thing. Better generalization is literally the same title, even though they... Yeah, the new unseen stuff here, I think. This one uses an example like understanding physics. A model pretends on general tasks like understanding physics. And then it doesn't continue the analogy. It would be good if this said, like, understanding physics often is more robust and adapts to play new unseen situations like molecular chemistry or hadron collisions or photonic encephalation. Improve performance and combining strengths. So this is a unique point. Getting stuck in local minima. Poor local minima. You gotta avoid getting stuck in poor local minima, man. That's a tweet. It's a tweet. Tweet it. Let's see if you can do it. Tweet it. This is what clearly would do for you, man. Siri, send tweet. Improve performance helps it get stuck in local minima. Combining strengths means that we can, put it together with this. I'll let it slide as its own. I'll let it slide as its own unique idea. Data efficiency is its own unique idea. That we probably could combine with combining strengths because, yep. And then modularity sort of ties in with this, so at the end of the day, this one does give me more information, but this one is not bad. This one has unique information, like mentioning data efficiency here, that is not mentioned here. So I think this, I don't know if this is what MOE really is, but I think this, these methods where people use a variety of models to generate a bunch of results and then a sort of orchestrator model to bring them all together into a final response seems like a really, straightforward, but, and maybe computationally expensive, but kind of robust solution to, getting the best out of all the different, models that all these different companies are building. So to close, I guess I'll say, one, thank you to Google for putting me to work. I charge $35 an hour. So yeah, that would be great. And I think obviously you guys can't afford to do this to everyone all the time, and I think people wouldn't do it. And I think a lot of people just shake it off because the pressure is quite high to review these kind of things. But I think if people can just take a good attitude with it and really just, benefit from the Feynman technique and just read it once, try and understand it. If you don't understand it, try and understand it, more. And then once you get it, you can move it on to the next idea and test and see if you can kind of link them together and understand the context. If not, you can go back. It's a great method of learning, and I really recommend it.